Hello everyone, this is Himabindu from the Department of CSIT. Today in this video, I would like to explain about the conversion of finite automata from the regular grammar. So here we have to convert the finite automata, we have to convert the regular grammar into a finite automata. And there is a equivalency of conversion between the regular grammar and finite automata. So in this video, we would like to explain about the conversion from the finite automata to the regular grammar. So what is the procedure to convert from finite automata to the regular grammar? We'll see. So here let us take m is equal to q and sigma and q naught and f and delta. So these we already discussed. This is about the finite automata phi tuple. So finite automata, it is having a phi tuple for NFA and DFA, NFA and epsilon NFA. So for every finite automata, we have the phi tuple. So based on the transition functions and final states, these are the differences we have for the DFA and NFA and epsilon NFA. So here in this video, we would like to convert finite automata into a regular grammar. So what is meant by regular grammar? So how it is formed and how to derive a language from the given regular grammar. So these regular grammar and definition we already discussed in the previous video. And here we can assume that there is a grammar which contains, it is a 4 tuple. So in this 4 tuple, what is meant by V? In the sense it is a non-terminal set. V is a set of non-terminals. So here we will denote it as a capital A and capital letters. So we non-terminals which are represented by capital letters. So to differentiate between the terminals and non-terminals, we are writing like this. And T represents, it is a terminal. So those are small letters. And S represents, it is a starting symbol. And P represents the productions. So here these are the, this is a finite automata and we have to convert that into a regular grammar. So what is the procedure? So here we have to equalize this finite automata onto a regular grammar. So there is an equivalency between the regular finite automata to, we can convert a finite automata to regular grammar, finite automata to regular grammar, that is RG. So here we can convert from regular grammar to finite automata, and we also convert the finite automata into a regular grammar. So this is the equivalency between the finite automata and the regular grammar. So in this video, we would like to explain about the finite automata to regular grammar. What is the procedure? So here we have to equalize these two tuples, like M is nothing but it is a finite automata and Z is nothing but it is a regular grammar. So we have to equalize these two tuples. So first tuple is Q, as we already know that it is a set of finite states. So here these set of finite states is equal to the V which is having the non-terminals, and this Q is equal to V here. We have to compare both the two, That why? Because we have equalizing. So we are converting the finite automata into a regular grammar. And here sigma, which is having the input symbols which is equal to terminals. No, terminals which are small letters. So we are equalizing this. Sigma is equal to T and here Q is equal to V. And one more, Q naught is a transition initial state. So here the initial state we will represent it as a S. And here it is equalizing. Q naught initial state is equalizing to the starting state. And production delta is equal to productions. So we will write it as a productions. We have to convert a finite automata to a regular grammar. So here these are the things, only one thing left, final state. So when we reach the final state in the transition diagram or transition functions, when it is the state, it is reaching the final state, we have two cases. So here what is the first case in the sense? So here what are the productions? So here delta is nothing but here we are represent it as a production. So how to represent a production? So let us take a Q naught as an initial state and it is having the input symbol A and it is reaching the final state, that is a QF. So here it is with the input symbol A, it is reaching the final state. So in this kind of situation, we have to represent the production rules. For this one, P is equal to starting state. This is the starting state. We can say that S and it is reaching the final state with the input symbol and QF is the final state. So here in this kind of situation, we have to write starting state to A also. So when it is reaching the transition function, when it is reaching the final state, we have to represent the production rules like this. S tends to A with the input symbol and the final state. And one more production rule, S tends to terminal, we have to represent. And when this is a final state. So and one more case is case 2. So transition of Q naught comma A tends to Q1. So this is not a final state, not final state. So when this kind of situation occurs in the finite automata, we have to write the production rules. S tends to, so this is the S starting state and S tends to A. When we are giving the A as an input symbol, it is reaching the state Q1. So this is when we have to write the terminal, when the state is not a final state. So when it is a final state, we have to write the two productions. And here when it is a not final state, we have to write the one production for this one. So like this, we have to write equalize this all the tuples. First Q is equal to, it is a finite set of states that is represented here in the grammar. So which is equal to the V. V is nothing but it is a non-terminal set. And here T is nothing but terminals which are represented in the small letters. Those are equal to the finite automata input symbols. Those are represented with the sigma. And starting state is equal to the Q naught initial state for the finite automata. And the P is the production rules, so which are defined from the transition function. So based on the finite automata, whether it is a DFA or NFA or epsilon NFA, it depends on the transition function. We will form the production rules. And here when it is reaching the final state, the production in the transition function, the state which is reaching the final state, it has the two productions So what are the two productions in the sense? The state with the input symbol along with the state name and with the terminal symbol. There are the two productions. And when it is reaching the non-final state, it is having the only one production, that is S tends to AQ, AQ1. So this is the procedure we have to convert a transition finite automata to the regular grammar. So let us explain more in detail with this conversion, how to convert a finite automata into a regular grammar. So let us take one finite automata. So we will write the finite automata. We have to convert that finite automata to a regular grammar. So what is the finite automata? So here we are taking the DFA diagram, transition diagram. So it is having the two states with the input symbols A, B. So here, so this is the transition diagram where we have, in this one, first step what we have to do in the sense, we have to identify the phi tuple for this one. So let us assume this as a finite automata as a M. So and what it contains in the sense, so here Q. So Q, let us write first what is the phi tuple for finite automata. So final state and Q naught initial state and delta and sigma. So here Q is equal to, so how many states are there? Finite set of states. We have Q naught comma Q1 and initial state is Q naught and sigma is equal to, what are the input symbols? So here A, B, A, B. So what is the input symbols? A comma B. And transition functions we have to write, and a final state is Q1. So here I am writing final state is equal to Q1. So here is the phi tuple. So in this one, first write the transition functions. So transition functions for each state we have to write. So transition of Q naught comma A as an input, it is going to a Q naught, and transition of Q naught comma B, it is going to Q1, and transition of Q1 comma A, it is going to the Q1, and transition of Q1 comma B, it is going to the Q1. So here is the transition functions. So for next step, what we have to do in the conversion of finite automata to a regular grammar. So we have to equalize this one. So Q is equal to, in the previous slide we discussed, we have to equalize these two tuples. So Q is equal to here V, and so let me write Z is equal to grammar. Regular grammar contains the four tuple. What are those? V, T and S is the starting state and the P are the production rules. So here Q is equal to V. So V is equal to, what is the states? Q naught comma Q1. And next, what is the equalization? So here terminals are sigma, which are having the A comma B. And so, and the starting state is equal to the Q naught and P we have to write. So here, what is the two cases? We will write one more time. The transition of state with the input symbol, it is reaching the final state. It should write the production rules AF comma S tends to A. And when it is a non-final state, transition of S comma A, non-final state, so S tends to AF, we have to write A and F, non-final state. So these are the two conditions we have to remember. And here, so when these are the transition functions we already have. So let us try to write the production rules for this one. So here the production rules for this transition of Q naught comma A. So here the transition of Q naught comma A, it is reaching the non-final state. So how to write the production rules for this one? Let us assume Q naught is equal to A, Q naught is equal to S. Why? It is starting state, start state, and Q1 is equal to A. So why? Because in tuple of grammar, we represent the V as a capital letters, and here we will take initialization. So S tends to, so here this one, so S tends to, S is Q naught, S tends to A, and which is reaching the state, same state. So it is not a non-final state. So S tends to A. We will A S we will write as it is. And next one is, so when it is having the input symbol B for the same state S, so B is reaching the final state, and final state is represented as, this is the final state. So B is represented as A as a represented as a final state, and so this is the final state. So when it is reaching the final state, we have to write the two productions. What are those? In the sense, S tends to with the input symbol, with the input symbol B. So we have to write the production rule like this. And for the this kind of transition function which is having the production rules. So here we given the two inputs for the this S state, starting state, A is over and B is over, and next state we have to take A state, and let us assume Q1 as A, and A tends to, when we are giving the A as an input, it is reaching the final state. So it is reaching the final state. What is the final state representation? A. So, and we have to apply the two production rules when it is reaching the final state. So what is the input we are having for this one? And when we are giving the B as an input, it is reaching the final state, and with this representation and along another production rule B. So here this is the regular grammar. So regular grammar which contains, let me write regular grammar, language of regular grammar is equal to, so 5 tuple, so 4 tuple, what is that 4 tuple? V is having S comma A and B, and sigma is equal to sigma which is represented with the terminals A comma B, and S is the starting state S, and next to last production rules which we will write as a S tends to AS, and we will write all this. So we are writing this in the same line with the mod S B A comma B, and A tends to AA B A comma B. So like this we have to write the production rules for the given finite automata. So this is how we converted a finite automata into a regular grammar. And one more example. So we have to convert a regular grammar into a finite automata. So we will write the regular finite automata Q naught. So, and here in the previous video, previous slide, we take only 2 states. Now we will draw 4 states. Let me write what are the state names. So Q2 and Q3. So Q3 is the final state and Q naught is the initial state, and with the input symbol 1, and it is reaching the 0 as an input, it is reaching the Q1 state, and for every input symbol we have to write the where it is reaching the final state. So where it is reaching the next state, for every input symbol where it is reaching we have to assume. And for the input, it's 0 is there and 1 we have to write. And for this one also 0 is given and what we have to write here. and this is about the transition finite automata. And now we will convert this finite automata into a regular grammar. So what is the procedure? In the sense, we have to write the first phi tuple for the finite automata, and we have to equalize that to a regular grammar 4 tuple. And first, so what is the grammar contains? So finite automata, so which is having phi tuple. So phi tuple, what is the states? So q is equal to, so this is the q, q0, q1, q2 and q3. So this is the q, and we have to write the term sigma is equal to, this is the sigma, and 0 comma 1 is the input symbols, and and q0 is the initial state, and final state is q3, and transition function. So let us write the transition functions. So transition of q0 comma 0 as an input, it is reaching the state q1, and transition of q0 comma 1, which is reaching the state q0, and transition of q1, which is having the input symbol 0, it is reaching the q2, and transition of q1 comma 1, it is reaching the q1 comma 1, it is reaching the q0, and transition of, for every state, for every input, we have to write the transition function, and q2 0 as an input, it is reaching the final state, that is the q3, and when it is having the q2 0 1 as an input, it is reaching the state q0, and transition of q3 comma 0, so it is reaching q3 comma 0, it is reaching q3 itself, and transition of q3 comma 1, it is reaching q3. So these are the transition functions what we have written, and now next step is what we have to do. We have to equalize that 4 tuple, 5 tuple to a 4 tuple. So how to equalize? In the sense, q is equal to v, so that is having the states q0, q1, q2 and q3. So let us write it as a equal to S, A, B, C. How many states? 4 states. So four states, non-terminals. Those are non-terminals. And next, sigma is equal to terminals which are equal to 0 comma 1, and start, and q0 is the initial state, it is equal to S, that is q0. And next, for production rules, what we have to write. So production rules, so let us write here. So here I will write after sigma q0 is equal to S, and production rules, here production rules. So for production rules, how to convert that production rules to a finite automata to a production rules? In the sense, for every transition function we have to write the production rules. So let us, this is S and q1, so let us write S, A, B and C. So S tends to 0 as an input, it is reaching the A as a state, and A is not a final state, so we will write as it is. And q0, so S tends to 1 as an input, it is reaching the initial state S only. And this transition function q, and so A is equal to, we have to write, it is reaching the second state with the 0 input symbol B, and this is written as A tends to, with the 1 input symbol, it is reaching the S, and this q2 is a B, so B states to 0 as an input symbol, it is reaching the final state. Here what we have to write in the sense, C is the final state. So when we are reaching the final state, what is the production rule for this one? In the sense, we have to add the terminal symbol also for this one. So here the terminal symbol is 0 and this is the 0 input. And here for the B state, and when we are giving the 1 as an input symbol, it is reaching the Q naught, that is S starting state. And for the C state, 0 as an input symbol, it is reaching the final state. So when we are having the final state, we have the two productions, so 0 C and 0 input symbol, and C tends to 1 C with the 1 input symbol. So here what we have to do, so let's summarize this. S tends to 0A, 1S. So we are writing, instead of two equations, we will write the one equation. So here 0B and 1S. And from the state B, 0C, capital C, 0 and 1S. And from C state, 0C, 0, 1C, 1. So these are the production rules which are converted from the finite automata transition functions. And we will write the regular grammar for this one. So what is the phi tuple contains? So it is having the A, S, A, B, C and terminal symbols 0, 1 and 0, 1 and the starting state S. And what are the production rules? So production rules are, so S tends to 0A, 1S and A tends to 0B, 1S and B tends to 0C, 0, 1S and C tends to 0C, 0, 1C, 1. So these are the regular grammar which we have converted from the given regular finite automata. And here in the next video, so these are the references. In the next video, we will like to explain about the conversion of a regular grammar to a finite automata. In this video, we converted so finite automata to a regular grammar, and we will see the equivalence of this finite automata and regular grammar in the next video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.